We process information at the speed of light, but we communicate at the speed of biology. For decades, voice technology failed to bridge that gap. Humans speak at roughly 150 words per minute. After a sentence, biology dictates a 200 to 500 millisecond pause. If that extends past 800 milliseconds, our brain registers a broken connection. Legacy voice assistants operated with an unnatural 3 to 5 second delay. Engineers reached sub-second latency by dismantling the sequential processing pipeline and forcing every component to run concurrently. Cheating that 800 millisecond latency limit is the specific engineering milestone that transitions an AI from a command line utility into an active conversational agent. This diagram outlines the 2026 cascading pipeline architecture. The entry node, speech-to-text, translates raw audio into transcripts under 300 milliseconds. That text routes into the large language model. Here, the primary metric is time to first token, emitting a response in roughly 200 milliseconds. This strict timing requirement dictates model routing, using small, optimized models for 80% of interactions and larger reasoning models for complex triage. Finally, the third node, text-to-speech, converts the LLM's text tokens back into a natural-sounding audio waveform in 40 to 75 milliseconds. Even with these highly optimized individual models, running them one after the other still violates the 800 millisecond biological threshold. In a naive approach, each stage waits for the previous to finish, guaranteeing a 3-second delay. Streaming architecture solves this. Speech-to-text emits partial transcripts every 20 milliseconds. The LLM executes speculatively on those chunks, while text-to-speech synthesizes simultaneously. All three streams run in parallel. Total perceived latency is no longer the sum of all stages, but roughly the latency of the slowest single stage. Concurrency is the engineering trick that creates the illusion of instantaneous thought, mathematically collapsing 3 seconds of compute into 400 milliseconds of perception. This concurrent pipeline relies entirely on one fragile gatekeeper, voice activity detection. The VAD decides exactly when the system should listen and when it should act. VAD operates as a state machine, transitioning from quiet to starting to speaking, and finally into the ending state. The ending state is where implementations fail. When the user stops talking, the system starts a timeout clock, usually set between 600 and 800 milliseconds. If engineers set that timeout too short, the system triggers a false positive. The user pauses to collect their thoughts. The VAD incorrectly assumes they are finished, and the AI cuts them off to answer half a question. If the timeout was too long, the system creates a false negative. The user finishes speaking, and the system waits in silence. The perceived latency doubles. Basic VAD simply measures acoustic silence. Modern systems rely on semantic endpointing, analyzing the partial transcript in real time to determine if the turn is actually complete. Advanced orchestration layers use a predict and scrap technique. The system speculatively triggers the LLM during a pause, but instantly dumps the generation if the user resumes speaking. Without flawless state management at the endpointing level, the fastest AI models in the world will still feel like a broken phone tree. Enterprise voice agents interact with the real world. They book appointments and pull records. Every time the system reaches out to an external database, it introduces a massive new latency penalty. This function call requires an intent pass, API execution, and a response pass, creating 1 to 3 seconds of silence. Developers mask this through intent prefetching. Additionally, orchestrators use backchanneling. A secondary layer of filler audio, like "let me check that for you," injects into the timeline, naturally masking the empty gap to buy compute time. High-volume deployments utilize response caching for repeated queries. If most callers ask for directions or pricing, the system serves pre-synthesized audio, dropping the TTS latency to 0. Achieving real-time interaction requires masking back-end computational limits with deeply human conversational psychology. The cascading pipeline has an architectural alternative: native speech-to-speech models. These systems discard the text intermediary entirely, processing audio directly through the neural network. Native models maintain raw acoustic data. They hear laughter, detect frustration, and interpret vocal stress. When deployed over high-bandwidth WebRTC internet connections, they offer extreme emotional intelligence and very low latency. Curious, framing the problem, If native multimodal models are faster and smarter, why do over 90% of production call centers in 2026 continue to use text-based modular pipelines? The constraint is the physical infrastructure of the public switched telephone network. Standard phone lines aggressively compress audio down to an 8 kHz frequency. This 8 kHz compression destroys the acoustic fidelity required for native models to detect emotion, neutralizing their primary advantage over modular systems. This chart compares the cost over time for both architectures. The cascading pipeline maintains a predictable, flat cost. Because native models lack a text intermediary, they must reprocess the entire audio context on every turn, exponentially driving up compute costs. Architectural selection is dictated entirely by the deployment environment. WebRTC applications favor native empathy, while telephony demands modular control. Even a perfectly concurrent software pipeline cannot outrun the speed of light. Routing a signal across continents adds severe network delay to the execution time. Production deployments require regional edge architecture. Voice agent servers must be geographically co-located with SIP trunks to eliminate cross-network latency hops. Deploying voice agents at scale is now primarily a distributed systems and networking challenge. Every optimization, from streaming tokens to endpointing state machines to edge routing, serves a single uncompromising master: the 800 millisecond threshold of human connection.